Good morning, everyone. Welcome to the second day of the OpenCoast tutorial. I'd just like to inform you that all the lessons are being recorded, so don't worry if you miss something, but try to not be late to the sessions and enjoy the tutorials. Thank you.
Welcome to the second day of the OpenCoast User Training course. I'm Alberto Azevedo from the National Laboratory for Civil Engineering in Portugal. The lectures from the first part of this course are available at the OpenCoast's website. The second day will be focused on understanding how to use OpenCoasts for 2D with waves and currents and 3D forecast simulations. The last day, the third day, will be focused on developers training. In the first two modules, Anabela Oliveira and I will present you some insights about forecast systems. And afterwards, my colleague André Fortunato will also present how to use OpenCoast to generate 2D and 2D waves and currents forecast systems. After a short break, my colleagues Marta Rodrigues and André Fortunato will explain how to use the OpenCoast service to generate 3D forecast systems and how to manage the systems that you create, and also to see the results with the OpenCoast Manager and Viewer. We will close this training with your evaluation to our performance in this course. I remind you that we will have some periods to raise questions. Please raise your question in Zoom and wait for the moderator to give you the stand. State your name and affiliation when asking the question, and ask the question in English. Please be concise to give opportunity to other colleagues to ask questions. You can also type your questions in the chat directly. We will answer it directly in the chat during the session, or if time allows, we'll give you the opportunity to place your question during the questions period. Please avoid being late to the sessions and remain silent during the lessons with your microphone muted. The organizers will be around during the breaks and in the end to answer any additional questions you may have. Please enjoy the tutorial.
Hello, I'm Anabela Oliveira and I am a researcher at LANEC. In this module, we will review forecast systems importance and present the OpenCoast service. In the first lecture, we will start with the importance of forecast systems and present a methodology to create them for accurate and robust results. We also set the stage for the need for an on-demand forecast system platform, OpenCoast. The second lecture explains the concept behind OpenCoasts and also the registration steps for using the service. Then, in the next three modules, we will focus on the three main components of the OpenCoast platform. In modules 7 and 8, we will present the configuration system, where the user sets up the forecast system for the different circulation options, 2D, with and without waves, and 3D forecasts. Finally, Module 9 presents the other two components of the OpenCoast platform, the Forecast Manager, where we can manage all our forecast systems, and the Outputs viewer, where the forecast results can be visualized and compared with field data.
Hello, I'm Alberto Azevedo from the National Laboratory for Civil Engineering in Lisbon, Portugal. And in this lecture, I'm going to present to you some insights about forecast systems. In this presentation, we will talk about the importance of water forecast systems and why we need them, the stages and main blocks that constitute a forecast system, the strategy used to build and operate a forecast system, the water information forecast system WIF, developed and operated at LNEC in the last decade, and the difficulties inherent to the development of these systems and their major challenges. Forecast systems are particularly useful to many tasks. For example, to anticipate extreme events such as storm surge that can lead to inundation in coastal areas, extreme swells that can interfere with port activities and have severe erosion impacts on the coast, oil spills, or other water quality hazards that can have huge consequences to population and ecosystems in coastal areas. They can also support emergency actions to mitigate the effects of these events. Forecast systems are also management tools. They support decision makers' management to take actions to reduce the risk in coastal areas. Finally, these tools promote the blue growth of the European economy by supporting daily economy tasks at the coast, such as port or fisheries activities, as well as leisure and recreation, such as surf or sailing. The main role of a forecast system is to predict the water conditions for the next 2-3 days. Therefore, a forecast system is composed of 4 main blocks. We need to represent the reality as close as possible, so we must force our system with the boundary conditions and make the system evolve. Winds, tides, waves, water stratification. Then these forcings are used to generate predictions at our domain of study using calibrated and validated hydrodynamic models. In order to estimate the quality of the predictions, automatic comparisons with in situ data must be made using available online monitoring stations data. And finally, the results must be presented to the user in a friendly way. For this task, WebGIS platforms are the most intuitive choice. The OpenCoast Daily service generates 48 hours forecast for water variables, and a WebGIS interface provides access to model prediction and field data. In order to build and operationalize a forecast system, we must consider the relevant physical processes that occur in the study domain. We have also to identify the relevant spatial scales to represent these processes in the area of interest, implement the numerical models, calibrate them, and then validate the results using the historical field data at both stages. All of these previous steps are necessary to implement an accurate, robust, and reliable forecast system, which can be useful to anticipate extreme hazard events. These resulting forecast systems, when linked with monitoring networks, can help us develop contingency methodologies for distinct applications for the estuarine and coastal areas, with characteristic scales and processes well represented. In terms of forcings, several options are available at atmospheric forcings. Here, I'm going to briefly overview those used in OpenCoasts. GFS is a worldwide global forecast system provided by NOAA. It has 0.1 degree of spatial resolution. Forecasts are also available from the model ARPEGE, developed by Météo France for the European coast. This system has the same spatial resolution of GFS. Both systems provide forecasts of the mean sea level pressure and the wind components at 10 meters of height. For the oceanic boundaries of the OpenCoast forecast system, several options are available. The first two options is the FAS 2014 tidal model and the PRISM 2017 models. The main difference between the two is on the representation of the atmospheric pressure. FAS 2014 provides the amplitude and phase of 34 tidal constituents but no atmospheric effects. To overcome this limitation of FAS, PRISM takes into account atmospheric effects at the ocean boundaries through the inverse barometer effect. The two products also have different application areas. FAS 2014 is applicable to any coast, while PRISM can only cover a part of Europe. In summary, PRISM should provide a better representation of the mean sea level at the coastal zones, but it can only be applied in a limited area. Its results are more accurate in the Iberian Atlantic coast. OpenCoasts also has the option of using CMEMS, the Copernicus Marine Environment Monitoring Service. This service gives us products to force the coastal forecasts. Both CMEMS Global and EB are available, providing 3D forecasts of baroclinic circulation. CMEMS Global covered the whole globe at 112 degrees resolution, while CMEMS EB provides a finer output of 136 degrees, but only for the Iberian Biscay-Irish area. LNEC has been working in numerical modeling systems for over 2 decades now. In the last 10 years, we have dedicated some effort building forecast systems in order to respond to our customer needs and studies. During this period, several tools and modeling modules were built which lead to the creation of WIF, LNEC's Water Information Forecast Framework. All forecasts were developed based in this core component. WIF is also at the heart of OpenCoast service. The WIF platform can be applied to any coastal system, incorporates all relevant processes in an integrated way, from circulation to water quality in a cross-scale approach, from river to ocean, including the urban dimension, and provides automatic predictions and alerts. The present slide shows several examples of application systems developed by LNEC. Wave propagation in the North Atlantic and in the Portuguese coast, tides and storm surges in the North Atlantic, wave current circulation and inundation in the Tagus estuary, 3D baroclinic circulation in the Aveiro Lagoon, 3D baroclinic circulation in the Faro Lagoon. Regarding the wave current circulation and inundation in Tagus estuary, in this particular case, use the CHISM WWM MPI-based modeling suite, which is implemented in OpenCoasts. In spite of their importance, forecast systems present several challenges and difficulties. These issues have been limiting their worldwide application to all coastal systems. Let me summarize the top issues. Forecast systems development requires mixed teams with experts in both numerical modeling and information technologies. They required significant effort for development and maintenance. This is valid for the modeling systems as well as for the computational infrastructures. To be robust, forecast systems need to be redundant. This is necessary to minimize failures. Finally, they require computational resources every day. Guaranteeing these continuously available resources can be complex on a case-by-case basis. So, we built OpenCoasts to address these main problems. This platform aims to minimize these difficulties for all users that need forecast systems by developing a service to implement forecast systems, providing computational resources, managing output files generated daily, and making the development as flexible, quick, and easy as possible. Thank you for your attention. In this lecture, we will provide an overview on OpenCoasts, starting with the motivation and context for its development. We will then present the main properties of the OpenCoasts platform, as well as its architecture and interfaces. Finally, we will guide you through the first steps on how to start using the service. Why do we need OpenCoasts? Presently, site-specific forecast systems present several difficulties. They are complex to develop and maintain. They require mixed teams, experts on coastal processes and numerical modeling, and also information technologies people. They require a major effort to build and operate, and it's very complex to upgrade them for new developments. Computational requirements are common to all forecasts. How is it going to be supported? EOSCAB Resources provides the right framework and opportunity to make forecasts available to all. With these services, we manage to abstract the users from those difficulties. Users will be able to dedicate their valuable time in research or daily tasks of their jobs without having to think about computation resources or other needs to take advantage of a forecast system. The OpenCoast platform implements forecast systems for a system chosen by the user, using a user-friendly web interface, allows the choice of the processes, model, and forcings, allows the replication and change of forecast systems, avoids the need of a large team to generate forecast system, and take advantage of the European Open Science Cloud, EOSC, to provide the required computational resources through the EOSC Hub project. The OpenCoast platform is organized along three axes: the common dependencies that are commonly used in our forecasts, the user-specific dependencies that are related to the particular site and forecast conditions selected by the users, and finally, the OpenCoast engine that integrates the front end and the back end. The front end is the interface that allows the user to create a deployment of a forecast, manage and visualize the forecast results. The back end deals with the model operation and information and other control actions needed in the forecast. OpenCoast has strong requirements. For redundancy, real-time operation, and timely forecasting, significant computational power is needed to address the needs of many users. Similarly, a tool for on-demand usage produces considerable sized outputs, thus requiring a large storage capacity. These features justify the use of the European Open Science Cloud support. OpenCoasts is organized along three components. The first is the configuration assistant. It guides the users through the generation of a forecast system, provides help, and provides basic quality control operations. The second is the forecast manager, dedicated to monitor and making changes to existing forecasts. Finally, the viewer that facilitates the access to forecast outputs. To start using OpenCoasts, one needs to register at the platform site. This registration is confirmed by email and is evaluated by the platform administrators. After approval, a confirmation email is sent and the user can start using OpenCoasts. The user information is kept confidential and it's only used to compute resources used per country in an aggregated way. Now, I would like to walk you through your first use of OpenCoasts. You must first log in at the platform site using the credentials selected at registration. As this service entails real-time operation based on user-selected choices, the users must first accept the conditions of access. Then the platform proposes a tour on the functionalities to facilitate its use. If you don't want to see these, just hit close. You can always go back and look at these instructions. The platform provides two types of help, shown here in simple or more detailed information. The access is available at the buttons shown. This closes the first lecture. Thank you for your attention.
Hello, everyone. Good morning again. Now it's time for you to ask any questions you may have on the OpenCoast and this brief introduction. I'm here and along with my colleague Alberto Azevedo, which were the people giving the lectures.
Before we start with the questions, I would like to say that there's a typo in the presentation. Well, two things. First, there's a typo in the presentations. The GFS model from NOAA has a 1/4 degree resolution, not the value that's shown in the slides. And the second one, the second information I have to give you is that in the last days, due to maintenance operations, the data from CMEMS, the global data from CMEMS is under maintenance. So if you start some forecast systems in OpenCoast with this forcing, please be aware that the simulations may take some delay due to this fact. So that was the 2 points that I would like to say. Now for questions, if you have any questions about the forecasts and the platform. If not, we could follow the lectures, and you may place the questions in the end of the morning.
You can put it in the end, or during the sessions, you can put them in the chat. So we will try to answer them live, okay? Well, if there are no questions, we'll proceed with the next lecture. Thank you.
Hi everyone, this is André Fortunato from the National Lab for Civil Engineering in Lisbon, Portugal. In this set of tutorials, we will show you how to generate a coastal forecast system using OpenCoasts. In this first part, I will address the simplest possible case, a forecast system for 2D depth average barotropic flow without waves. In spite of its simplicity, this case already has most of the ingredients that you will find in the more complex configuration, so it's a good starting point. OpenCoast guides you through 7 simple steps to generate a forecast. Throughout the procedure, you will see a figure showing those 7 steps. The step you are in will be highlighted in blue, as you can see here for step 1. The steps are the following. In step 1, you must select the model and the configuration. Then in step 2, you're going to define your domain by uploading and verifying your grid. Step 3 is devoted to the definition of the boundary conditions. Then in step 4, which is not mandatory, you will define the output stations. Finally, steps 6 and 5 are used to define the physical and the numerical parameters used by the model. You end up in step 7, where you can review all the work that you did and finally submit your simulation. In the following slides, I will show you how to provide the required information at each of these steps. So, starting at step 1, you must select the model configuration. You can select between 2D barotropic, that we will address in the present tutorial, 3D baroclinic, and 2D waves and currents. You will also choose the model version and the duration of each forecast simulation. However, in the present version of OpenCoasts, there is a single choice for each of these items. When you are done, you hit Complete Step, and you are taken to the next step in the procedure. You can always come back later if you want to change anything. In step 2, you define your domain by uploading a finite element grid that you must have previously generated. The grid is provided in the format used by Schism, which is also the same format used by other models like SELF or AdCirc. The simulation will be performed in geographical coordinates, but you can choose to provide the grid in Cartesian coordinates if you want. OpenCoast will transform the grid for you. Together with the grid, you must indicate the coordinate system either through an EPSG code or by choosing one of the EPSG codes that are available. In addition, you must also specify the vertical reference of the grid, specifically the vertical displacement between the grid bathymetry, and the mean sea level. When you hit complete step, OpenCoast will show you the grid in the WebGIS. This allows you to check if you provided the correct coordinate system. You can also check if the boundaries were correctly defined, as they are shown in different colors. Once you check the grid, you can move on to step number 3, in which you will specify the boundary conditions. Now, there are three types of boundaries. At the ocean boundaries, you have to impose the elevations and the velocities. At the river boundaries, you'll specify the discharges. And finally, at the surface, you may specify the atmospheric pressure and the wind. So first, for each boundary, you need to define which type of boundary it is. You tick each box and hit define type and forcing condition. In this particular case, all the open boundaries are ocean boundaries, so they can be defined simultaneously. When you click on define type and forcing condition, you see this pop up where you can define the boundary as each boundary as an ocean or a river boundary. For river boundaries, you'll have to specify yearly or monthly discharges. If you have a source of data, either from a watershed forecast model or from measurements, you can provide a URL where this information will be provided every day. You can also specify a discharge at a particular boundary as being a fraction of the discharge at another boundary. At ocean boundaries, you can choose one of these sources of information. FES 2014 is a global tidal model. CMEMS Global is a global model that simulates 3D flow, and the others are local models that you can use for the Iberian region. Finally, for the atmosphere, you have the choice between GFS, which covers the whole globe, and ARPEGIE that covers Europe with a better resolution. These choices are made in the boxes at the bottom of the screen. Now, in step 4, it's the only one that is not mandatory. You can skip this step if you want, although in general, you'll probably want to have outputs at specific stations. OpenCoast automatically shows you the tidal stations that are available at EMODNet that are either inside your grid or relatively close to the grid. Those stations are shown as blue circles on the map. Those that are inside the grid are further circled with a dashed line. You can choose these stations by simply ticking the boxes. In addition, you can specify your own stations. For instance, in this case, there is a station just outside the grid because the grid does not have enough resolution at this island. So I picked a point inside the grid, but close enough to the real station so that it makes sense to compare the model results with the data. Now, in step 5, you'll have to specify the physical and numerical parameters. Most of them are fixed in OpenCoasts, so you can see what the choices are, but you cannot change them. By clicking on Customize Parameters, you can change two parameters, the ramp-up period, that is normally set to 1 day, and the time step, whose default value is 30 seconds. If you aren't familiar with Schism, you may find this value to be too high. However, Schism is a semi-implicit model, and it's very stable. We therefore tend to use larger time steps than in other models. Now, some parameters vary in space. That's the case of the friction coefficient that can be either constant or spatially varying. So in step 6, you define those parameters. Specifically, you can specify the mining friction coefficient. If you want it to vary in space, you'll have to provide an additional file with that information. That file will have the same format as a grid file, but with the mining coefficient instead of depth. Otherwise, you can simply use a value constant in space. So at this point, we have provided all the information that is required. So in step 7, you can review the choices that you made and you can go back if you want to make any changes. For instance, if you click on Domain, you'll see your grid again. Now, once you're happy with all your choices, you must provide a name to your forecast, accept the terms and conditions, and activate the system. At this point, your forecast is up and running. Your first forecast will be done within 24 hours, and once the first simulation is complete, you will receive a confirmation email. So I hope that you enjoyed this tutorial and you've seen how easy it is to generate a coastal forecast system. In the following tutorials, we'll add some complexity by including waves and baroclinic processes. Thank you. Hello everyone, this is André Fortunato at the National Lab for Civil Engineering. Welcome to the second tutorial on the generation of ocean forecasts using OpenCoasts. This tutorial will focus on the generation of forecasts of waves and currents. As you will see, generating a forecast with or without waves is very similar. So I will assume that you have already seen my previous tutorial on the generation of 2D circulation forecasts. If you have not watched my previous tutorial, I strongly recommend that you do so before watching this one. Here, I will focus primarily on the differences between the two. So in this case, we will follow exactly the same steps as before. Most of the steps will actually be identical. A few steps will be slightly more complicated since we will need more information. In particular, steps 3 and 5 are the ones that change the most. Step 1 is the same as you saw before, except that now you have to choose the 2D waves and currents run type. Now step 2 is also the same as before. However, the grid must now be provided in Cartesian coordinates, at least for the time being. Hopefully this is a problem that we will address in future versions of OpenCoasts. Also note that we can only provide wave boundary conditions for the North Atlantic Ocean, so at present simulations are restricted to this region. We're using a different test case to illustrate the use of OpenCoasts in this case. So in step 3, you're going to specify the boundary conditions. So the difference is that now you have to provide not only the elevations and velocities at the ocean boundaries, but also the wave spectrum. The source of this spectra is LNEC's forecasts of waves in the North Atlantic, and you'll choose it in this tick box. The North Atlantic wave forecast is obtained by running the model WaveWatch 3 in the unstructured grid that you see here. The resolution is about 0.1 degrees in European coasts and 0.5 degrees elsewhere. Winds are taken from NOAA's GFS, and the model is run for 25 frequencies and 24 directions. The model is cold started every day for 7 days into the past and 2 days into the future. Those 2 last days of simulations are used to provide the boundary conditions for the local models. Coming back to the generation of the forecasts, we are now at step 4, in which we define the output stations. Again, this step is very similar to the one I showed previously in the previous tutorial. In step 5, we now have to provide not only the physical and numerical parameters for the circulation model, but also for the wave models. So this page is split in two different tabs. On the left, we have a tab for circulation, which is identical to the one that I showed you in the previous tutorial. But now there is an additional tab on the right where you specify the parameters for the wave module. Again, most parameters are fixed with 2 exceptions, the time step and the wave breaking coefficient. Step 6 is where you specify the spatially varying parameters. It is exactly identical to the case without waves, so I won't repeat the details. And we're coming to step 7, where you submit your forecast. As you saw, there is some additional complexity in OpenCoasts when you include waves, but overall it is still reasonably easy to use. So thank you for watching this tutorial, and I hope that you enjoyed it. At this point, you can try to use OpenCoasts yourself, or you can watch a video of me doing it. Once you are comfortable with the 2D options, you can move on to the third tutorial of this series on 3D baroclinic circulation. Hi everyone, this is André Fortunato from the National Lab for Civil Engineering in Lisbon, Portugal. In this video I'm going to show you how to generate a forecast system for waves and currents using OPENCOASTS. So I am assuming that you have already registered in our site, so all you have to do now is to log in with your username and password. When you log in, you are taken to the forecast manager, so you have to move to the configuration assistant where you can generate your forecast system. At the top of your configuration system, you're going to be seeing the 7 steps that you have to go through to generate your forecast system. The step you are in will be shown in blue, so we're starting at step 1. In step 1, we're going to specify the model that we're going to use. We're going to choose the 2D waves and current model. I have to choose the only option available, Schism version 5.4.1, and we're going to be doing forecasts of 48 hours. When you hit complete step, you are taken to the following step. In this case, step 2, in which you're going to specify the domain. To specify the domain, you're going to provide a grid, a finite element grid that was previously generated. In this case, it's a grid for the Leixões Harbour in the north of Portugal. Together with the grid, you have to provide the coordinate reference system for the grid. You can either specify directly the PSG code or select one from the list if yours is on the list. You also have to specify the vertical reference of the grid. So in general, you'll specify the vertical displacement in meters between your grid bathymetry and the mean sea level. So in this case, it's 0. If you want, you can also ask OPENCOASTS to suggest a time step for your simulation, and this time step will be generated based on your grid. So you hit complete step, and OPENCOASTS is going to show you your grid in a WebGIS, and this is done so that you can check that your grid is okay. So basically, you see the grid here, you see the bathymetry, you see the open boundaries, so you have an ocean boundary here and then 2 smaller river boundaries. There's one here and one in the small river that discharges into the harbor. From the WebGIS, you can see that the grid is at the correct location, so everything is fine, and we can proceed to step number 3. In step number 3, we're going to specify the boundary conditions. So you see the 3 boundaries here. For each of them, we have to tell OPENCOASTS whether it's an open boundary, whether it's an ocean boundary or a river boundary. So boundary number 1 is an ocean boundary. Boundary number 2 is a river boundary. So you have to hit river and specify river flow. In this case, this is the Douro estuary. We're specifying 100 cubic meters per second. Boundary number 3 is a very small river, and we're going to specify 5 cubic meters per second. Now if you go down the same page, you get to choose the sources of information for your boundaries. First, for the circulation model, we have several choices. We're going to choose FES 2014. It's a global tidal model. For the waves, we use our own North Atlantic WaveWatch 3 forecast. And finally, for atmospheric forcing, we're going to choose Arpège from Météo France, which covers all of Europe. So now we're going to move on to step number 4. Now step number 4 is the only step that is not mandatory. You can choose to skip this step if you want to. But in general, you'll probably want to have outputs at different stations. So to start with, you're shown all the stations from EMODNet that are within or close to your domain. In this case, there's only one. It's the Leixões tide gauge. So we're going to choose this one. But in this case, we're going to choose a second station, a virtual station. We'll pick it here. We're choosing this station because there's a wave buoy, so we're going to call this station wave buoy. It's a virtual station, and there's no data to compare with. So if you know the exact location of the station, you can correct these values here. So these are our two stations, and let's move on to the next step. Step number 5, we're going to specify the physical parameters, the physical numerical parameters. We now have two tabs, one for circulation and one for waves. Part of the parameters are predefined. You can look at them, but you cannot change them, and some of them are customizable, so you can select other values if you want. So we have a ramp-up period in days. The default value is 1 day, and there's a time step. The default value is 30 seconds, but since in step number 2 we asked OpenCoast to provide suggestion for a time step, OpenCoast computes this value 36 seconds. We're still going to go with the reference value 30 seconds, and we're done with the circulation parameters. For the waves, we have to provide a time step. Here we're going to choose 5 minutes, so 300 seconds, and you can change the wave breaking coefficient, which by default is 0.78. So we're done with the first set of parameters. Now we have a second set of parameters, which are the parameters that can vary in space. In this case, we have the mining coefficient, so the friction coefficient, which can either be fixed or variable in space. If you want it to vary in space, you have to provide an additional file which has a grid format, except that instead of depth you'll have the mining coefficient. As an alternative, you can specify a constant value, which by default is 0.025, but you can change it here if you want. And we're done. We've specified everything that was needed. So at this point you can look at your choices, so you can go back and change them if you want. And if you are satisfied, you have to provide a name. You have to accept the terms and conditions. You can provide a description if you want to, and that's it. You activate the system. Okay. So at this point, the forecast system has been generated. It's activated, and the first runs will be done tomorrow. You'll receive an email once the first simulation is finished, so that you can go to the viewer and look at the results. So as you can see, generating a forecast system with OpenCoast is fast and very easy. So that's all for now. I'd like to thank you for your attention. I hope that you enjoyed this video. Goodbye. Hi everyone, so this is the point where you get to ask questions if you have them. Well, I think the videos were clear. Anyway, I think you just need to try to run OpenCoasts, and if you run into any trouble, there is plenty of help. There are plenty of help buttons. So if you don't have any questions, Annabella, back to you.
We're going to stop now for a short break of 15 minutes. So we'll see you again at 10:45. So see you then.
Hello, my name is Marta Rodrigues. In this lecture, I will talk about using OpenCoasts for 3D circulation forecasts. As for 3D forecasts, there are 7 steps that the user needs to complete to deploy a 3D forecast. Step 1, select the model and the duration. Step 2, upload and verify the grids. Step 3, specify the boundary conditions. Step 4, define the output stations. Step 5, define the physical and numerical parameters. Step 6, define the spatially varying parameters. Step 7, review and submit. So, the first step is the selection of the model, and in this case we must select 3D baroclinic. The next step is the upload and verification of the grids. The upload of the horizontal grid is similar as in 2D. The user uploads the grid and indicates the coordinate reference system for that grid. For 3D forecasts, the user also has to upload a vertical grid. At the moment, only SD vertical grids are available. In this step, the user can also choose to calculate a suggestion for the time step, which is based on the characteristics of the horizontal grid. After the completion of the upload of the files, it is possible to verify the uploaded horizontal grid, as you can see in here. The next step is the specification of the boundary conditions. The user must select the boundaries using the tick boxes and specify the boundary conditions for the ocean, the river and the surface boundaries. For 3D forecasts, besides specifying elevation and velocities at the ocean and the river flows, the user must also specify the boundary conditions for salinity and temperature. So starting with the ocean boundaries. For these boundaries, the following options are available. For water levels, the user can select FES 2014, CMEMS Global, PRISM 2017 or CMEMS EB models. For salinity and temperature, 2 options are available, CMEMS Global or CMEMS EB model. To set up the atmospheric forcing, the GFS model forecasts are available. Regarding the riverine boundaries, 4 options are available to specify the river flows. The user can specify yearly or monthly flows. You can also provide your own source of forecasts, as you can see in this example, or you can specify the river flow as a fraction of another river boundary. In this case, you have an example in which the river flow is 5% of the open boundary 2. For salinity and temperature, 2 options are available. The user can either specify monthly values, as you can see here for water temperature, or yearly constant values, as here in example for salinity. The next step is the definition of the output stations. This step is the same as in 2D forecasts. ModNet physics stations inside or close the grid are proposed to the user. The user can also add or other real or virtual stations. A limit of 5 stations per forecast is imposed. Step 5 is the definition of physical and numerical parameters. Most of the parameters are fixed and predefined. However, there are a set of parameters that can be customized. For 3D forecasts, these parameters are the method for computing velocity at nodes, the horizontal viscosity option, the Shapiro filter, the minimum water depth for wetting and drying, the implicitness factor, the warm-up period, and the time step. The next step is the definition of the spatially varying parameters. The available parameters are the drag coefficient, the albedo, the water type, and the temperature and salinity initial conditions. There are 2 options available to define these parameters. The user can either upload a file in grid format or specify a constant value. Finally, step 7 is the last step. The user can review the previous choices, name the forecast, and activate it. This is the end of this lecture. Thank you for your attention.
Hello, my name is Marta Rodrigues. In this video, I will show you how to use OPENCOASTS to set up a 3D circulation forecast. Please note that access to 3D simulations is granted on request. So if you want to do 3D forecasts, please send an email to the email that you can see here in the page. Okay, so if you already registered to the system, you can start a forecast by doing login. When you do login, you can see the forecast systems manager, and to set up a forecast we need to go to the configuration assistant. Okay, so we are now in the configuration assistant, and you can see in the top the 7 steps that we need to follow to set up a forecast. So first we need to select the model, then in step 2 select the domain. In step 3 we need to set up the boundaries. In step 4 we can choose some stations for data comparison. In step 5 we can set up some parameters. In step 6 we need to add some additional data, and finally in step 7 we can complete our forecast. Okay, so let's start by step 1. So I am going to do a forecast for an example for the Tagus estuary, and in this case we are going to do a 3D baroclinic forecast, and we are going to choose the model, schism, and the period, which is a 2-day period. Okay, step 1 is complete, and we move to step 2. In step 2 we are going to choose the domain, so the horizontal grid, and in this case, since it is a 3D forecast, the vertical grid. So let's start by choosing the horizontal grid. That should be in a schism format, and also the vertical grid. Okay, we also need to select the coordinate reference system for the horizontal grid, and let me just choose here, and also the vertical displacement, if any. In this step, we also can calculate a suggestion for the time step if you want to. I'm not going to do that now. So we can complete the step, and after a little bit, we can see the model domain and check if the uploaded grid is fine. Okay, so here we are, and you can see now the grid here. You have some information on the top about the number of nodes of the grid and elements. You can also see the boundaries, the ones that are open, and the land boundaries. So this step is complete, and we can move to the next step, which is the setup of the boundary conditions of the grid. So here in the right you can see the boundaries of the grid. In this case we have 3 open boundaries, here and here, and what we are going to do now is to set up the conditions for these boundaries. So starting with open boundary 1, this is an ocean boundary, so we need to define the type and the forcing. So in this case is ocean, and we need to set up the forcings for circulation and also for temperature and salinity for this boundary. So I'm going to choose, for in this case, CMEMS EBI, and also the same forcing for temperature and salinity. Next, I'm going to set up the open boundary 3, this one. This is the Tagus River in this case, and so I'm going to select a river boundary. So for the river boundaries, we need to input information about the flow, the temperature, and the salinity. For the flow, we can set up an annual flow, a monthly flow, or give a source of flow forecasts, which is what I'm going to do in this case. So I just need to put here an URL with the source of forecasts. This file must be in the flux.th schism format. I also need to set up the temperature boundary conditions, and in this case I'm going to use a monthly climatology, so I need to input here the values for each month, and I'm doing that right now, as you can see. Okay. The final 3 months, and that's it, the monthly climatology. And we also need to set up the boundary conditions for salinity, and in this case I'm going to use a constant value of 0. Okay, with this we set up this boundary and we do define. Okay, you can see here now we have all the information for this boundary, and we are just missing open boundary 2. Open boundary 2 is also a river boundary. So we do need to set up the flow, the temperature, and the salinity, but in this case the flow will be a percentage of open boundary 3, and again for temperature we are going to use climatology. So let me just put here the values. Okay, almost done. Okay, so monthly values, and finally for salinity, again we are going to choose a constant value. Okay, you can do define now. So right now you can see that all the open boundaries have the forcing set up, and what we also need to do in this step is to set up the atmospheric forcing. We can choose either no forcing, or what makes more sense for this type of applications, forcing, and in this case GFS forecast system. So with this we can complete this step, and we can move to the next step, which is step 4. And in step 4 we can select some stations for data comparison. We can either choose some of the available stations that are displayed, or we can also choose other virtual stations. So in this case, I'm just going to choose one of the proposed ones, and I'm going to use Cascais Tidal Gauge, and with this we can complete this step. Step 5 is the definition of the parameters. Parameters can be predefined, or we can also customize some parameters. Here are some of the parameters that can be customized. Let's just see the time step. Time step is by default set up for 30 seconds, which makes sense for the application, and I'm not going to do any change in the parameters for this application. So we can complete step 5, and now in step 6 we need to add some additional data. And that data is the drag coefficient, the albedo, water type, initial conditions for temperature, and for salinity. So we can either upload special varying files, or we can set up a constant value. So for the drag coefficient, I'm going to upload a file, so I need to choose the file. This should be in grid format. Okay, for the albedo, I'm going to use a constant value. The same for the water type. Again, I'm going to use a constant value. For the initial conditions of temperature, I'm also going to choose a constant value. And for the initial conditions of salinity, I'm going to upload a file with a special varying salinity from the ocean to the river. Okay, so with this we can complete step 6, and we are now proceeding to step 7. And in step 7 we can review our forecasts, the 7 steps. So we can see here the domain. We can also review the choices for the boundary conditions, the stations that were selected, and the parameters. And here you can also see or download the param.in file, and finally the additional data. Again, we can either see or download the files. So what we need to do next is to give a name to the forecast. Okay. And a description if we want to, and finally we accept the terms of and conditions of use, and we can activate our forecast. So when we activate the forecast, we receive a message, and please note that the first results will only be generated within the next 24 hours, and after that you can consult them in the outputs viewer. Okay, so this is the end of this demo about using OpenCoasts to set up a 3D circulation. Okay, so hello everyone. So this is Marta Rodrigues. We have now periods for a couple of questions if you want to. I'm seeing we have a question in the chat. I can try to answer that about the values for the monthly climatology. So in that specific case, but for any given case, if you have data about the river input or about the the ocean input, if it makes sense, you can use that data and make a climatology, do a monthly climatology. So it must be a site-specific climatology so that the values make sense if you have that data. I don't know if I answered your question, Magnum. Okay, I don't know if there are any other questions. And if you want to, you can continue, or if you have other questions later, you can continue to put those questions in the chat. Okay, I think we can proceed.
Hello, my name is Marta Rodrigues, and in this lecture I will talk about the Outputs Viewer. The Outputs Viewer provides access to maps of scalar and vector fields, time series, and download of the model results. It is organized as follows. The forecast systems are listed in the left panel. The time series are displayed in the center panel, and the maps are available in the right panel. So, let's start with the left panel. The user can choose the variables that want to see in the maps, can also choose the stations and the variables that wants to see in the center panel, and can download the output files. The maps are displayed in the right panel, as you can see here. For the maps, the user needs to select the variables that wants to see and the vertical level in 3D applications. There are several functionalities available on the map. Namely, the user can zoom and pan, can also define the virtual stations to see the time series, and can choose the background map, and finally can also see some animations of the model results. The central panel displays the time series. As for the maps, the user needs to select the variable and the vertical level in 3D applications. Here you can see an example of the time series display. The user can see time series of water levels, velocity, significant wave height, peak period, salinity or temperature. The graph also shows the instant of the time series that corresponds to the map. In this panel, the user can also print graphs and download the model results in CSV or Excel formats. This is the end of this lecture. Thank you for your attention.
In this lecture, we will present the main functionalities of the Forecast Manager. In the Forecast Manager, the user is able to monitor the forecast execution, perform some operations over forecast, such as start, stop, deactivate, clone, etc., print a report on forecast configuration, and request an extension period for each forecast system. There are many possible states for each forecast. Step K indicates that this system is in construction. We can continue the configuration later or just eliminate it. Active, in this state, the forecast system is running and we can deactivate it, clone it, or check it. Deactivated is that in this state the forecast system is not running. The user can reactivate or delete it. The user can check the status and the settings of each forecast system in these areas. The user can clone or duplicate the forecast system in order to change the boundary conditions, input parameters, or outputs. The user can reactivate a deactivated system or delete it, and return to the configuration assistant to continue the setup of the forecast. To clone a forecast system, the user only has to click on the clone button. Then the OpenCoast generates a duplicate of the selected system with a new ID, and afterwards the user can change the settings of a new system. In this example, we could change the value of the Manning coefficient. Then, saving the changes, and finally, launching the new forecast system. When operating the OpenCoast platform, the user receives several warnings by email or through the interface. These warnings help the user to make sure he's doing the intended action and follow their deployments closely. Examples of these warnings are when a system runs for the first time, when a status change is requested, or when the user requests an extension period for this forecast. Thank you for your attention.
Hello, my name is Marta Rodrigues. In this video, I will show you our OpenCoast Outputs Viewer. So we are now in the Outputs Viewer. You can select the Outputs Viewer on the top right menu of OpenCoast, and the Outputs Viewer has three main sections. So in the left panel you can see a list of your forecast systems. In the center panel you can see some charts, and in the right panel you can see the results of your run in maps. So the left panel gives you access to this information. So you can select which variables you want to see in the maps in the right. You can also select the data or the model results that you want to see in the chart. And this panel also gives access to the output files of your forecast. So here you can see a list of the outputs of the forecast, and you can download these files. So let's start with the maps. So to see the outputs of a forecast in a map, you need to select which variable you want to see. So I'm just going to select temperature, and since this is a 3D forecast, we also need to select the vertical level, in this case the surface. So now we have the output in the map, and we can do zoom in or zoom out. We can also choose the background map, and we can here in the bottom navigate in the run, so we can see another time step. Okay, and here you can see the values of the legend of the outputs that we are seeing. Okay, here we can also select some stations other than the ones that we have previously selected during the setup of the forecast using this button, and we can put here another station. When we do that, we need to select which variables we want to see in the charts. And since this is a 3D run, we also need to select which vertical level. In this case, I'm choosing the surface. And if we do head, we can see the time series of the variables here in the center panel in the chart. So the water levels, the velocity, the temperature, and the salinity. We can add more stations from the map, or we can also see the outputs from the previously selected stations. To do that, we need to go to the left panel and select a given station. Again, we need to select which variables we want to see. I'm going to choose the same, and again at the surface we do add, and now we have two time series in the chart. For the elevation, you can see here some differences for the velocities, the water temperature, and the salinity. In the chart, we have this line that show us the instant that corresponds to the map, and we can also see the value at a given time step. In this menu, you can also select if you want to print the chart, or you can also download the time series. So this was a brief overview of the Outputs viewer from OpenCoasts. Thank you for your attention.
Now we are open for some questions about the configuration panel, the forecast manager, and the Open Viewer, and other questions about the platform that you may have. Just to summarize from the questions in the chat, for the ocean boundaries and atmospheric conditions, we get all the data from the services available from Copernicus or NOAA or other providers automatically every day. For the river flows, we have to put it in the boundaries like you saw in the videos, for the as an average or for each month of the simulations. To clarify, the user, when you state a forecast, you have a default period of 1 month for each forecast. Each user may have 5 forecasts at the same time due to restrictions in the computational demands. So you run these 5 simulations. If you want more, you have to eliminate one of them to create another. There is also a limit for the number of nodes in your grid. I believe now is 175,000 nodes. So there's a limitation for that. And the system, after being prepared and launched, the system prepares each day. It gives you 48 hours of forecasts for that period of 1 month. If you need more time, you have to send an email to us to analyze your case and give you the extension period for 1, 2, 3 months or 1 year if you needed that. This is just restrictions due to computational resources.
Okay, so I don't know if we don't have any more questions, and meanwhile, maybe I can add that in the near future, we have plans to extend the OpenCoast services. We are now starting H 2020 funded project, the project EGIAs, and we are going to improve the service to include other functionalities. We are going to include the possibility to do incasts or scenarios. So if you don't want to do a forecast, but you want to study some processes related with climate change effects, for instance, we are going to improve the service to do that type of analysis, and we are also going to extend the service for water quality. We are going to first to include variables related with fecal contamination and microbiology, and we will also give the possibility for the user to simulate any or a given tracer. So if you have a tracer and you want to simulate it, you can also you will also be able to do that in the new improved service that we think that will be available by the end of this year, 2021. Okay. So I don't know if Alberto, you want to say some words about tomorrow? Or?
Yes, I would ask Gonzalo to put the last slides. Now we are going to. I ask you to do the evaluation questionnaire to evaluate our performance in this course, how you enjoy this course. Today we are finishing the users training. Tomorrow is the developers training. The link for the evaluation questionnaire was sent by email to you. So I'll give you some time for that. For tomorrow, the day is focusing developers training, and sorry.
Sorry, Albert. Maybe I can speak a bit about tomorrow's day. So we will have
Okay.
we'll have a session just for developers, or mainly for developers, not on the modeler side like today. We will discuss a bit how it was developed the front end side of OpenCoasts on the first session. Second session will be directed to the back end, where all the models or all the deployments are run, executed on a daily basis. And in the end, we'll have an infrastructure presentation from LEAP side. And just to remind you, it's mainly for developers, but everyone is welcome to assist and to view the presentations and to ask questions and learn a bit more.
Okay, so this is the end of today's lessons. Thank you so much for your participation. For those of you that could not have the opportunity to grade us, do evaluate our work. Your comments and feedback is very important. And do try the OpenCoast platform. And if you want, feel free to send us an email with suggestions and things that you think that can be improved. So for tomorrow, we have, for the first time, a course dedicated for people that want to implement OpenCoast at their own infrastructure, or to want to participate in the development effort. So it's more geared towards computer science people, but everyone is free and welcome to attend. Again, tomorrow we are going to have an evaluation, and by the end of the whole course, you will have the opportunity and you'll get an email with the contacts from all lecturers and also the feedback that we got from all of you. Thank you so much for participating in the users training, and I hope to see all of you tomorrow. Thank you. And don't forget, we are going to be around for a while, so if you have more questions, feel free to ask them. We are here to answer them. Thank you.
Chefe, você está
Okay, everyone, since there are no more questions, thank you so much, and I hope to see all of you tomorrow. Goodbye.